Hey everyone, welcome back to my channel EduVibe. In today's lesson, we're moving on to the next topic of the electromagnetic radiations, which is the graphical analysis of the photoelectric effect. So we done the photoelectric effect topic in the previous lesson. Today we're doing the graphical analysis in this. So which is important, very important after analysis. We do two graphs which relate to the something else with the photoelectric effect that all connected to this topic. So let's move on to the first graphical analysis question. The question, like two graphs we have. So this is the first graph of that. So we saw the equation that we derived from the photoelectric effect using the law of conservation of law of energy. So which is that formula? We done that E photon is equal to the W plus E K mass. We done this formula. If we rewrite this, and if we some expand this, so this that E photon is equal to the H times frequency, which is a Planck's equation, which is again equal to W plus EK METS. So we have that thing. Let us examine the typical graph of the photoelectric effect showing that the maximum kinetic energy, which is that, of the electrons as a function of the frequency of the incident electromagnetic radiation. So we compare this with the frequency and we have a maximum kinetic energy. You will see we have this kind of graph. It goes from like a negative thing towards the positive thing of the y-axis. So you can see the graph of the maximum energy as a function of the frequency. So what's they telling about this graph? So we have something theory of this behind the theory of that. The user conservation of energy and the curve stretching, we can look at see the what the graph tell us. Rearranging our equation of the maximum kinetic energy of the electrons and relating to the linear equation. So EK mass should be in your y-axis, so it should be isolated, and we have HF and minus W, which is in your kind of, you can say, the work function, but not like the frequency. Okay, we have like this type of thing now, EK mass with this. So in the Y you have a EK mass, in the X you have a frequency. Your slope is equal to the H only, not the HF, because F is your x-axis, and you have also have a y-intercept, which is minus W. So that's B. From here you can do this in the math too, that this is equal to ms plus b. Your m is your slope, which is h. X is your x-axis value, which is f, plus b is your uh, y-intercept, which is over there is minus W. So that's all in way down in the table too. So the slope of the graph leads to a Planck's constant in joules per second. Why the joules per second? Because we have a kinetic energy in joules. So that's why it's joules per second, and the value you have to get with that. This is an experimental way of determining the h. The y-intercept of the graph yields the negative of the work function. Also, this is also in joules. H-intercept of the graph yields the threshold frequency required for the photon emission to occur in the hertz. So if you have a kind of question which relates to the maximum kinetic energy with the frequency, so you can make that type of graph, and you have that these things can be know from here that which thing is what, that what is the slope of that kind of graph. Slope is h. So we have a two graphs have different things, different slopes, and different all the things we have. So from here you can see this is like a first graph of the photoelectric effect, which is equal to which is compare the maximum kinetic energy with the frequency. So that's the thing, you get the questions from here too. Next thing, before starting with another graph, we have to know for that graph is the stopping potential. So something called the stopping potential is given by the Milklin's contribution, Milklin's experiment. So the stopping potential is the minimum electric potential required to halt the motion of the emitted electrons in a photoelectric effect, effectively counteracting their kinetic energy. So this is kind of minimum electrical potential which is required to hold the motion of the emitted electrons in a photoelectric effect, which affect the kinetic energy too. This relationship between the maximum kinetic energy of the electron and the stopping potential given by the, so we have a relation of this. So now again we have a EK max is equal to QV stop. This formula is given in your formula sheet 2, and this is formula for the stopping potential. And we compare this formula with another graph now. So for graphical analysis, using the conservation of energy and a curve setting, we look to see that tell us that what. So again, we have a photon is equal to the W plus EK max. and that HF is equal to W plus, now EK mass is also equal to something which is QV stop. We do the stopping potential formula in this. And when we arrange that in the form of this, which is Y is equal to MS plus V, you will have to know about something. Like we have to V stop, because over there your V stop inverse is in the Y axis and frequency is kept over there. So this is over there, and we get H upon Q, we rearrange them, F minus W upon Q. So that this one is your Y axis, this one is your X axis, this minus W upon Q is your B, which is Y intercept, and that H upon Q is your now a slope in that case. So that's the all thing in the table you will see, which I told you. Now the slope of graph yields the Planck's constant with EV dot S. Now is EV dot S because we have E in this, then we convert this with EV now. So we have EV value of the Planck's constant of this 1.41 into 10 to the minus 15 EVS. The method is from the Milk-Lane used to determine the experimental value for H. Y-intercept is your negative value of work energy in EV with Q, and X-intercept graph yields the threshold frequency required for the photo emission. That's all things are remains the same. But graph is different now. We have a stopping potential as a function of the frequency. So that two graphs are very integrated, not very integrated with each other, which have a different terms that have a mass magnetic energy, that have a stopping potential, which is a new term for you, and the new formula, which is that, which is we discussed over there. So that formula you have to know, that formula, that equation you have to know. So when you get the question, you just use that thing. You just use that thing to calculate your anything from here. Not do like too much work in this. And you have to know the tables too. The vision is what. So we also have one example related to stopping potential, because you get the separate questions related to the stopping potential. So we have to get question says that determine the stopping potential of a electron in the photoelectric surface as a work function of 1.30 eV. Incoming photon has a wavelength of 665 nanometers. Basically, I'll find the stopping potential. Stopping potential, to find this, we have like E photon is equal to the W plus EK mass. So we'll start finding the EK mass. I will tell you that what is the, how can you go to the E stop or V stop, which is the stopping potential. So we're calculating the EK mass from here, which is equal to E photon minus W. EK mass is equal to the Hc upon wavelength minus W. Put your things in that, so you can find the now potential stopping potential. So it will be EV. So 1.41 into 10 raised to minus 15 EV dot S 3.0 into 10 raised to by 8 meter per second. Divide this by the wavelength of 665 into 10 raised to minus 19 meters. Minus this by 1.30 EV. So when you calculate this, you get about 0.5676 EV. So from here you can see your potential, which is the stopping potential. So how this is equal to that E can be separated out, and you will get 0.5676 volts. When you put this like over there, that E should goes to charge of this, which is 1, and this goes to your V stop in volts. So basically your V stop is equal to, which is the stopping potential, is equal to 0.57 volts. Always when you telling that you have to find the stopping potential, you have to go like this. You have to find the EK mass, and EK mass is compared with the stopping potential, which is that you can compare like this and get your EV stop. So that's how you have to deal with. So you can't directly like go into, because you don't have Q. When you have Q, so you can directly use that formula. But for now, you can't use that formula. So to do like this. So that's all you have to do. And we doing that topic is done, because we're doing only graphs and the stopping potential topic. And this is very important topic for the graph point of view, for the stopping potential point of view. Because you get the questions like this more and more in that unit. So for now, this all for this lesson. So learning is where EduVibe, learn smarter, not harder. Please like, share, and subscribe to my channel. If you have any questions, like me in the comment section. See you in the next lesson. Till let's get it with EduVibe.